In this chapter, we will study about the relationship between the continuous time signal and its corresponding discrete time signal. Firstly, we will talk about the sampling theory. Sampling theory is how to converting continuous time signal to discrete time or discrete time signal into a continuous one. That is related to sampling theory. After that, we will study about the Fourier transform, continuous version, and the discrete version is a DTFT, discrete time Fourier transform, and that can be converted into discrete time Fourier transform and make it fast. We would like to study about the fast Fourier transform algorithms, and that is related to how to handle the discrete time signal in the spectrum domain. And the next one, we would like to find out the relationship between the Laplace transform, that's the continuous one, continuous domain. And in the continuous domain, the system described by its differential equation. But the corresponding discrete time domain is expressed by G transform. G transform is discrete time signal system, and that system described by difference equation. So basically it's the same idea, but one is a continuous domain, the other one is a discrete time domain. So we would like to figure out the relationship between what is the continuous domain property and the other one is how to convert it by by taking the sampling. It becomes a discrete time system. So we would like to figure out the relationship between continuous one versus a discrete one. We would like to figure out the relationship between them. Our first topic is a sampling theory. To understand the sampling theory, let's consider the first one is a continuous signal. That's the XCT, like this one. This one is continuous signal, and this continuous signal is sampled by periodic impulse train. That is called ST, is a sampling signal. Then it becomes the sampled signal XST. Here shows the relationship in the figure. XCT is a continuous signal. It is sampled periodically by use of the impulse train, and then it becomes a sampled one. You know what sampled signal ST is a period. A period is TS. TS is called sampling period. Okay, here is actually I think this should be. This is XTS. Okay, TS is sampled period, sampling period. So XST is basically periodic signal. So we can express this one into a Fourier series because it is a periodic signal. So how are we going to express that in the Fourier series? To express Fourier series, we need to find out the Fourier coefficient. In the delta function, Fourier coefficient is 1 of TS. You know what it's a Fourier coefficient CK is 1 over TS. It's a period, and during the one period, we have to calculate this one. K, JJK, omega S, T, dt. Where that omega S is defined as 2 pi times 1 over TS. Okay, so K omega S, like this one is called harmony component. Okay. If you calculate this one, due to the delta function, it is non-zero only t equals 0. So by definition of the impulse signal, it becomes 1 of TS. So all Fourier series coefficient is 1 over TS. Then we can express this impulse train into like this way. Coefficient is 1 of TS. So some K changing from minus infinity to the infinity, and e to the JK times omega S. We can express this one into this way. This is a Fourier series expression for the same signal. Because it's a periodic one, so we can express into a Fourier series expression. So anyway, continuous signal is converted to sampled signal by use of this sampling signal. By this processing, you know that this switch can be expressed as a product. You know that if it is non-zero, then it is connected. If it's zero, it's disconnected. That can be expressed by these product equations. So if t equals to nts, then it has value like xc and ts, but otherwise it's zero. Then this continuous time signal times this sampled signal st will become the xst. So here shows that the xct converted into xst, and the time difference between the sample to sample, this time difference is ts. So signal is sampled every ts second. At here, we assume that the continuous signal is band limited like that. This means that the continuous signal has some finite bandwidth. It can be understood like this way. By taking the Fourier transform at you know what, here omega is 2 pi f. Okay, you can understand that way. Xj omega is a Fourier transform of xt. So Fourier transform okay, xt t dt. Okay. This is definition for the Fourier transform. By taking at here, I need to consider this subscript c is continuous signal. So this is also continuous version. The means of this band limited signal is this one. So xct value is non-zero only in between these bandwidth. So omega m. So omega m is a maximum frequency that can contain at the xct signal. So this means that all the other frequency component is zero, only exists between the minus omega m and omega m. This is maximum frequency component. So this is the definition for the band limited signal. You need to understand the meaning that if it is not band limited, we cannot make it sample. So to make it sample, we need to in somehow make it band limited signal. So to make it that one, later we will talk about the anti-aliasing filter. By use of anti-aliasing filter, we can make it any certain continuous signal to have a band limited one. So this is a pre-assumption that that satisfied sampling theory are working. So this one, you need to understand what's the meaning of band limited signal. How are we going to make it band limited one? That is a later topic. So by use of filter, we can make a band limited signal. The meaning is this one: maximum frequency is omega m. So after the faster than is 0. Okay, and the sampling period is ts, and the sampling frequency omega s, as I talked to you, that it is defined 2 pi over ts. Sampled signal is just a product between the continuous signal and the sampled signal between them, and then it can be expressed in this way. For these given conditions, we would like to understand the Fourier transform of xst, Fourier transform of sampled signals. To find out the Fourier transform of this one, first consider the st. So st is given as an impulse train. We would like to take the Fourier transform of this one. By use of delta function, we can find out that this Fourier transform of the sampling signals. We can refer this original definition for the Fourier series expression. You know what impulse train is a periodic one that can be expressed by the Fourier series. If you look at here, the Fourier series shows that these definitions, the exponential function is 2 pi times delta function in the spectral domain, so you can easily find out the Fourier transform of st. So we find out the st, and xct, let's assume that I talked to you that the xct is given like this way. It's given like that. the band limited one. That is our assumption. Okay, xc j omega is given. Then in the time domain, product becomes the convolution in the spectral domain. So in the Fourier domain, it should take in the convolution. By taking convolution, x j omega and s j omega will give this result. So it's a shifted version of spectrum. You know that omega is repeated every kth omega s steps. We can understand in different way. Okay, look at here in this approach. We would like to take a Fourier transform of xst, but xst can be expressed by the product between the st and the xct. Firstly, we using the delta definition of the st, but at this moment let's consider that it's the equivalent expression as a Fourier series. We can use this one to express xst, so we can refer to this one, some k changing minus infinity to the infinity, and xct e to the jk omega st. Okay, xst can be expressed by this way: xct nts times delta t minus nts. We can express xst in this way by use of definition of the impulse train definition. But the same signal can be expressed by use of its equivalent Fourier series expression. We can express the same signal in such a way. Then we can express, we can find out the Fourier transform by use of Fourier transform definitions. Fourier transform of a sampled signal are given like x s j omega are given xst. So okay, repeat. Okay, this is definition for the Fourier transform of xst. Okay, so I just would like to replace xst with this expression. Then it will be given okay, over ts and sum k changing from minus infinity to infinity, and the integral okay, xct see that e to the, let's consider this part. So minus j omega jk omega s. T is the same thing, so we can express that one into this way. J is a common factor, and omega, okay, T is also another common factor. So omega minus k omega s. Okay. Okay, this is the same things. I just replaced xs with this definition, and then it becomes, you can refer these definitions. What does this mean? Okay, from this part. Okay. Yep. Okay, look at these red blocks. This one is Fourier transform over xct, but the frequency is this one. We would like to find out the Fourier transform with this okay, this block. So we can write down this way. Okay, 1 over ts and sum k changing from minus infinity to infinity xc j omega minus k omega s. Okay, now compare the two results. This part, okay, yep. Okay, anyway, compare that these two things are the same. So we would like to interpret what's the meaning of this one. XCT is repeated every case harmonics of omega s, and the scale down 1 over Ts. It's the same things. You can compare the two things. So this one and this one is the same result. One used by use of time domain product becomes the convolution in the spectral domain, and the other one is just taking the Fourier transform by use of a Fourier series expression of the sampled signal. And then we can prove that these equations, we need to interpret these equations. This can be expressed by this way. Omega is changing along the spectral domain. Then XCT, we know that that's a band limited signal like this way. This should be expressed in this spectrum. Firstly, we assume that the XCT is a band limited signal, and Xj omega, as we have look at here, if you see here, this one is the impulse train in the spectral domain. Every case harmonics, it's a impulse function like that. So the output is given as a convolution between two signals. The convolution between XCT and Xj omega are expressed here. So this is the convolution result. By taking convolution, this one is repeated on each impulse, but scaled down 1 over 2 pi because of these definitions of convolution. So 2 pi will drop out, and the amplitude is A, and 1 of Ts is multiplied here. So the amplitude is scaled down 1 over Ts like this way. So the amplitude is scaled down that much because of this value. And 2 pi is cancelled out by this 1 over 2 pi factor for the convolution. And then the convolution means that this one is repeated, and every impulse is convoluted, repeated like that. Then that becomes this spectral. The same equation can be understood by use of these definitions. This one is the same things. So 1 over Ts scaled, and Xc is repeated every case harmonic of sampling signal. So originally the analog signal is this band limited signal. So analog signal is band limited one, and we have applied the sampling signal to here. Then after the sampled signal spectrum are repeated like this way. Then now look at what is meaning of the sampling. Continuous signal defined all times. So every time it has some values, but in sampled one, it has value and specific sample times at given times. This one is a time domain expression. Time domain sampled signal is discrete one. It is defined in specific times. But in the spectral domain, it contains the original information like this way. So in the spectral domain, the XCT information are included here, but that is repeated every the sampling frequency. Then carefully look at, it seems like that we can recover the original the continuous signal by use of discrete one. You can see here that the sampling is drop out many informations. We only taking at discrete times, so some information are dropped. But is it possible to is it possible to regenerate the original signal without the loss? So it is possible for some specific conditions. So then what is the condition to reconstruct the original analog signal without loss from the sampled signal? That is this one, that this spectrum does not change during the sampling process. Then we can filter out only this part. Okay, we can filtering out only this part. Then we can reconstruct the original signal without loss. So to satisfy these conditions, the maximum frequency of the analog one is less than this value. We call this one is the Nyquist frequency. So this is Nyquist frequency is one and a half of the sample frequency. The half point of sampling frequency is called the Nyquist frequency. If maximum frequency is less than this one, so bandwidth is less than Nyquist frequency, then we can recreate the original continuous signal without the information loss. If it doesn't satisfy, it can be drawn at here like this way. The spectral bandwidth is larger than Nyquist rate, then it cross over this Nyquist frequency. Then because of the repeated signal, the right side, this signal is also entering this region. So spectral is changed in this way. This is called aliasing. So we need the one requirement obvious that the band limited signal, the maximum frequency should be less than omega s over 2. So if it's satisfied, we can recreate. So this one is called the Nyquist criteria. So the sampling frequency is find out by this criteria. So at here you need to know that what is the aliasing. Aliasing, if the analog bandwidth is larger than the Nyquist frequency, then the spectral contents entering the crossover this Nyquist frequency. Then because of these equations, the signal, the spectrum is repeated in the every sampling frequency. Then in this spectrum will also cross over this region. So spectrum is destroyed by this way. It's a damaged one. So this phenomena is called aliasing. So if aliasing occurred, it is not possible to recreate original signal. Okay. Now consider the reconstruction process. It means that we would like to cut out all the other spectral component except the DC component. So that is the reconstruction process. Here shows that the reconstruction process. At here, the idea is this one. We would like to cut out only this component. Okay. So to cut out this part, we need to apply this kind of filter in the frequency domain. Okay. So bandwidth is limited by these two values. That is Nyquist rate. And if we producting in the spectral domain XS times HR reconstruction filter, it means that the HR J omega times XS will give XCT XC J omega. So that is this one. So if you multiply this box, this one is 0, so all the other the harmonic component are removed. Only this part are generated here. The amplitude is the scale down 1 of TS. So we give TS is the filter amplitude like that. Then we can recreate this one. This shows that how to reconstructing in the spectral domain. But what about in the time domain? What is the process in the actual time domain process? Here shows that the XS J omega times HR are equals to X continuous version. So in the time domain version, in the spectral domain product becomes a convolution in the time domains. XS and HRT, by taking convolution between them, that becomes continuous signal in the time domain. To understand the time domain behavior, let's consider these signals. We know that in the time domain, it's a rectangular pulse, like this kind of rectangular pulse. Amplitude is A. This is time domain, and this one is tau over 2. And the minus tau over 2. It means that the pulse width is tau. Pulse width is tau. By taking the Fourier transform of this rectangular pulse, it becomes the sinc function in the spectral domain. In the spectral domain, it expressed by the sinc function. Like that. Okay. This is your frequency. And in the zero frequency, the maximum value is this area. Okay, so it's A times amplitude times pulse width is tau. Pulse width is not tau. So this is the peak value at the DC, and the first null is given by 1 over tau. So it's a 2 pi over tau. This is the Fourier transform of rectangular pulse. What about if time domain is sinc function? Okay, I think here. So here is the time domain. If signal is a sinc function, the amplitude is A, and the first null point is tau. We would like to take a Fourier transform of this one. Then it can be expressed as omega. It should be a rectangular pulse. That's this part. Okay, this seems like a similar that way. So we can give this kind of rectangular spectrum in the Fourier transform domain. The amplitude is a product between A and tau, so the amplitude is A tau. And the bandwidth of this one related to 1 over tau. So this one is a pi over tau, and this one becomes minus pi over tau. So the bandwidth is 2 pi over tau. The bandwidth it means this one, 2 pi over tau. You can prove it by taking inverse Fourier transform of this one. You need to clearly understand these two processes. So consider this part. We take the product in the spectral domain by this rectangular spectrum mask. By this spectral mask means that the sinc function in time domain, the product in the spectral domain, frequency domain, means that the convolution in the time domain. Okay, that is shown below here. This rectangular spectral mask shown here. This is a rectangular spectral mask given like this way. The amplitude is Ts and the bandwidth is omega s. So bandwidth is omega s. By taking the inverse Fourier transform in the time domain, what will be the shapes? First, consider the peak value. Peak value can be found by this area. So producting Ts times, and the bandwidth is omega s. And by taking inverse Fourier transform, we need to divide 1 over 2 pi. Okay, then you can see here that is 1. Okay, this is 1. So you know that omega s is 2 pi Ts, 2 pi over Ts. So it is 1. And what about the first null? It is given as 2 pi over this bandwidth. So we can write down this one is 2 pi over omega s. Is the first null. By definition, it is a Ts. So this becomes the sampling period. So this sinc function are written over here. So at t equal Ts is the first null and amplitude is 1. That's this sinc function. Sinc function characterized by these two values. So this is the reconstruction filter impulse response. Okay, this one shows that the impulse response of the reconstruction filter is a sinc function. Then reconstructed one in the spectral domain is a product like this way. The sampled signal is produced by the reconstruction filter. It gives the continuous version 1. What about in the time domain? Time domain, it should be convolution between the impulse response of reconstruction filter and the sampled signal. That's shown here. The integration index should be minus infinity to infinity. Okay, this should be minus infinity to infinity. And then xct delta and the sigma is the definition of the sampled signal. Sampled signal, as we talk about, is expressed by this way. Okay, we use this definition. So that is replaced xst. Okay, so xst is replaced by sigma and xckts and delta tau minus ts and h reconstruction filter. So by taking the convolution, we can look at here that it is given by this way. This one is at a given 1k xct gives the amplitude, and this one is a sinc function. Sinc function is shifted every k harmonics. Okay, that's the reconstruction process. This equation can be drawn as a figure like this way. The convolution process are shown like this way. This is sampled one, that's this value, and convolution is this one, red one. Okay, this is the 1k. The next sample is this one. In the next sample, and we have shifted sinc function should be applied here, and the next one is this one, one like that. So every sample we convolute with a sinc function HR. That's the shifted sinc function. Then it is given like that way. We have to sum up them. So by adding all these values, we can reconstruct analog signal. The continuous signal can be reconstructed by this process. So this one shows that the reconstruction process.